Imagine you are on a train moving smoothly, and you toss a ball straight up. It comes straight back down to your hand. Now, imagine you are standing on the platform watching that same train pass. For you, the ball travels in an arc. Both observations are valid, but they highlight something fundamental about how we perceive motion and, ultimately, time. An inertial frame of reference for time is essentially a perspective from which the laws of physics, particularly Newton's first law of motion, hold true without the need for additional fictitious forces. In such a frame, time itself flows uniformly, unaffected by acceleration. It is the fundamental coordinate system used to measure durations consistently. The core reason an inertial frame is so important lies in Newton's first law of motion. This law states that an object at rest stays at rest, and an object in motion stays in motion with constant velocity, unless acted upon by an external force. In an inertial frame, this law is directly observable, simplifying our understanding of how objects move. The key characteristic of an inertial frame is this absence of acceleration. This means the frame is either at rest or moving at a constant and changing velocity. If a frame accelerates, like a car turning a corner, you feel a pushing sensation which is often described as a fictitious force. Time measurements in accelerating frames become more complex due to advanced physical effects like time dilation. Albert Einstein's special theory of relativity further clarifies this principle. It beautifully states that the laws of physics are the same for all observers in uniform motion relative to one another. This universality extends to fundamental constants, like the speed of light in a vacuum, which remains constant for all inertial observers. While time flows uniformly within a single inertial frame, its rate can appear different when compared between two different inertial frames moving relative to each other. This is the intriguing phenomenon of time dilation, where time slows down for an object moving at very high speeds relative to an observer. Crucially, within its own inertial frame, time always proceeds normally. So, how do we use this profound concept? We use inertial frames as the bedrock for understanding and calculating physical events with precision. When you are solving a physics problem, an early and critical step is often to choose an appropriate inertial frame where the analysis becomes simplest and most direct. For example, if you are analyzing a projectile's trajectory, you typically choose a frame fixed to the Earth's surface. For many everyday scenarios and calculations, this provides an excellent approximation of an inertial frame. It is important to note that a perfectly inertial frame, one completely free from any gravitational or accelerating influence, is an idealization, much like a frictionless surface. Our Earth's rotation and its orbit around the Sun, for instance, mean that a frame fixed to its surface is technically non-inertial, experiencing tiny, albeit usually negligible, accelerations. However, for most practical applications, it serves as a very good approximation. A fascinating cosmic rest frame can be approximated by measuring the cosmic microwave background radiation. This ancient light, a relic from the early universe, provides a universal reference point against which the motion of galaxies can be measured, offering perhaps the closest thing to a truly inertial frame on a grand scale. Understanding inertial frames of reference is crucial because it provides the foundational stage upon which all physical laws operate consistently, particularly for observations involving motion and the flow of time. It allows us to distinguish between actual forces and apparent forces, enabling accurate predictions and a deeper comprehension of the universe's mechanics. Without this conceptual anchor, our measurements of duration and causality would become inconsistent and potentially meaningless across different observational viewpoints, hindering our ability to describe the universe reliably.